Hey guys, so I'm going to show you guys how to perform protein saturated mutagenesis using a Python wrapper named Mutate X, which you can download from GitHub as you see over here. I'll put the link in the description. So basically, saturated mutagenesis is a useful technique to find amino acid substitutions that might lead to better binding affinity. So, for example, I'll show you guys how to perform saturated mutagenesis on an antibody to the N-terminal domain of the SARS-CoV-2 spike protein. So first, I'm going to show you guys how to install Mutate X. It's pretty simple. I'm doing this in Linux. I believe it should work similarly in Mac OS. So one thing you want to do is just copy and paste this. Just clone it, which we did here. Actually, I should go to my home directory. So as you can see, we actually already have it installed. I would install it on your home directory. Next thing you want to do is to log into the virtual environment. This will make it very easy to get all the files you need for running the job. I've been getting this error, but then when I used this command, I was able to log into the virtual environment just fine. So now we're in the virtual environment, which means that anywhere within any directory we could run this job. It doesn't have to just be in the Mutatex folder. So next thing you want to do is go to the folder where you have your PDB. So here I have it's called new.pdb. I'll open it up for you guys just for you to see. So this contains the antibody right here with the N-terminal domain of the SARS-CoV-2 spike protein. And we will be performing not only saturated mutagenesis on both of these chains, but because this is a two-chain structure, Mutate X allows us to find the interaction energy between residues that might be important for this binding right here. Yeah, so show you guys how to run it. So first things first, within our folder or our directory, we have a few things. We have a mutation list, we have a repair run file template, we have an interface run file template, and we have a mutate run file template. All these templates are provided by Mutate X. So what you can do is after you install Mutate X, they should be within the directory, and I would just put them inside of the directory that you are choosing to run the job from. So it contains these are basically the default things. So mutate run file. This is the repair file, and then the mutation list with all 20 amino acids. So I forgot to mention, but before you can run Mutate X, you need to install Foldx. So Foldx is basically an energy suite where and Mutate X uses Foldx to perform the calculations. So you just go to download academic license. You have to register, so you put a username and email your institution, and then yeah, that's basically it. And once you're done with that, you have to set a path to where you installed Foldx, and then you should be good to go. So the first thing that Mutate X is going to do is it's going to repair your PDB file. This will use Foldx repair PDB module, which optimizes the conformation of your crystal structure. It repairs residues with bad energies, uh, with unfavorable torsion angles, van der Waals clashes, and total energy. Your ASN, GLN, histidine residues are flipped 180 degrees. This is done in order to prevent incorrect rotamer assignment. And then residues with bad energies are identified by the software, and they're mutated to themselves along with their neighbors to explore different rotamer combinations to find the new energy minimum. So first I'm going to show you the commands for running. So first thing we want to do is write Mutate X, and we can do this because we are in a virtual environment, so no matter what directory I'm running this command from, it will run. We're going to put the name of our PDB, which is new.pdb. You can actually specify multiple PDBs. So for example, if I had new.pdb, if I had to.pdb, and then new 3.pdb, I would just put multiple models to let MutateX know that we're using 3 PDBs. This is helpful to account for protein flexibility and local conformational changes. So you could run, say, 100 nanosecond simulation, for example. You can take 3 snapshots, save as PDBs from the simulation, and then you can perform saturated mutagenesis on it, and MutateX will average the results for all 3 of the calculations performed on different conformations of the protein. In this case, we're just going to use 1 PDB. So my name is new PDB here. Sometimes this is necessary, sometimes it's not, but I like to do it just so that there's no errors. I like to supply the mutation list, and this is done with the M. I like to specify what Foldx suite we're using. So in this case, I downloaded suite 5. It's the newest one. R, we're going to put the repair run file template.x. Then we're going to provide the mutate run file. So the thing with this is that Foldx provides you with these templates based off of their recommendation and Foldx for how to run these calculations successfully under the default settings. So I wouldn't change anything because it's optimized as best as possible based on the experimental data when creating this algorithm. But I would just take the files from the MutateX directory where you actually installed it and put it into the directory where you're going to run the job, just so you have all the files and it could easily find it. Now this isn't necessary, so normally a regular saturated mutagenesis could mutate each residue at every position, and then delta G values would be calculated by predicting the free energy of folding upon the mutation as a difference between the estimated free energy of folding of the mutant and the original wild type residue. But because we have a 2-chain structure, we could actually also calculate the interaction energies. So not only will we calculate the changes of stability for each mutation, but we also calculate how a specific mutation might increase or decrease the interaction energy before the protein. Like I said before, this is extremely useful in affinity optimization, as we are able to see, okay, residue 2 is interacting with residue 5 and a different protein. So for example, the N-terminal domain of the SARS-CoV-2 spike protein is interacting with residue and the antibody. So say the antibody has a leucine residue, the algorithm here employed by Foldx will mutate to all 20 canonical amino acids, and they might find, for example, that a phenylalanine or a glycine or any other one of the 20 amino acids, by mutating the leucine to one of them, actually increases its binding with the N-terminal domain. As you can see, or that it would be extremely helpful in antibody optimization. So for vaccines, for example, you want something that binds tightly to its target. A lot of times this better binding affinity also leads to improved neutralization. So the first thing, so that's why we would specify the binding interface. But like I said before, the binding interface only works on a chain of 2 proteins, I believe, or a protein with 2 chains, I believe. So if you have multiple chains, it might not work, but I'm not entirely sure on that, as I've only tried it on 2 chains before. So just specify the binding interface of interaction. We're going to use the interface run file. Like I said, these are all provided by Mutatex. And then we're going to do this, that B there. That B there, I've had issues before. So inside of the manual, which I'll show you guys right here, Foldx, not Foldx, but Mutatex says that you can specify the binding interface like this. However, I've had issues in the past when I've tried this, it didn't calculate the binding interface. So I looked by doing, so as you could see, I'll just get rid of this here. If you do mutate X, it shows all the commands that are possible. So as you see, we can specify the number of runs, so how many times to perform the calculation. Foldx, or Mutatex, I should say, performs 5 runs. That's the default setting, so you don't have to really change that unless you want to perform more, which of course would be more accurate, but it would take more computational cost. P is extremely important. The -P, that specifies the number of processors you're using. I have about 24 processors, and saturated mutagenesis can take a very long time, especially if you're only using 2, 4, 8 processors, because it has to mutate every amino acid to each of the 20 performed calculations, do this for every residue in the protein, and then it has to do that 5 times total and average all the results. And if you have more PDB, so if you're using 3, it has to do that for 3 of them. So as you can see, it could be very computationally costly. You can provide a partial mutate list if you don't want to include all of them in the mute list. This is a -X for the Foldx binary. Sometimes you might have to specify where your Foldx is installed if you did not correctly set your pathway. You shouldn't have to specify the rota base file, as this should be done automatically by the Foldx binary. If I said that specifies the suite, repair run file, the mutate run file, and the interface run file, which are all supplied by Mutatex, and then the B, which was the binding interface command that I said. So let's just retype all this stuff. So mutate X, new PDB, mutation, the mutation list, suite 5, repair run file template, the mutate run file template, the interface run file template, the B right here to calculate the binding between the 2 proteins, and we're going to specify how many processors to use. P, I have 24. I won't use all of them, just have some backup, so we'll use 20 processors. So that should be good. We're gonna press enter. So we have a few errors, but looks like nothing major. It's checking files in the PDB. It's finding the mutation list. These are the 20 amino acids that it will use. Structure check and generation. It's making a repair directory. And now it's running the repairs. So as this calculation will take probably 1 day or more, I'll show you guys what. Here's a repair file or directory folder that it's making. So I'll show you guys what the completed run would look like. There we go. So after the run has been completed, we have a few directories. We have the repair directory, which we really don't do anything with these, just the models that have been checked. Mutations directory. So these are the checked repairs for all the mutation. First letter is the amino acid. Second letter is the chain, and then the number of the amino acid. Here is the good stuff, the results. So inside the mutation folder, I should say the results folder, we have mutation underscore DDGS and interface underscore DDGS. So interface is the values of the interface results, while the mutation is the folding energy stability calculations for each residue and each protein. So for example, if you're wanting to perform affinity optimization, trying to find better residues that could lead to better binding in an antibody, we would be interested in the interface directory. Here's the final averages. As you can see, the interaction energies between chain F and chain B. So here are some of the results. So I got chain A, or not chain A, but alanine in chain B, and that was residue 25. So if I open it, the first value, I have the interaction energies here, and because it was on one structure, I have no standard deviation. So as you can see, there's all 20 here. The wild type right here, 0. So these amino acids, the values for the interaction energies, which is under the average, is actually in the same order as your mutation list was specified. So for example, where's my mutation list? The first one would be glycine, alanine, valine, leucine, isoleucine, etc. So they would be printed out in this value. The good thing about Mutate X is that they actually have built-in ways to analyze these results. So I can bring up the tutorial again. There's a number of ways to analyze this. So for example, you can visualize the output, but with a heat map, for example, which looks like this. So you can see in red the mutations that made the stability less favorable versus the ones that made it more favorable. You can do this for the mutation, also the interface ones, so you can see, okay, which amino acids were favorable, which were non-favorable. A lot of times for the interface calculation, obviously the residues not by the interface where binding occurs aren't going to be very important for binding, so you're going to get results that are basically 0, so those won't matter. You can do a distribution, a stem plot, box plot, violin plot, scatter plot of the values. You can make histograms, which is very cool. So you can do built-in histograms to show, okay, if I mutate to proline, I have very unfavorable interaction energy. If I mutate to leucine, I have some favorable binding over the wild type value, which was Q here, which is 0. logo plot, and a bunch of other things. I'll put this in the description so you guys can check it out. And also I'll put the link to the GitHub to download Mutate X. Show you guys what heat map might look like. So you can see here, you could specify how many to be plotted on each thing. That's all in the manual. So that's basically how you run protein mutagenesis using Mutate X, which employs the Foldx energy function. If you have any questions, please leave them down in the comments. If you like this video, please like and subscribe. Thank you.